Hey everyone, today we're looking at stars. In today's video we're going to describe a little bit of how stars work and try and understand some of the characteristics of stars and what they're made up of and kind of everything we can understand about them. So to begin, what exactly is a star? Well, a star is an extremely massive ball of glowing, hot, on fire gas. This gas is mainly hydrogen. There is some helium and other trace elements mixed in there. But you'd say about 99% or more of every star, when it begins its life, is hydrogen. Our sun also happens to be a star. Our sun is referred to as a main sequence star, and it has a mass that is 300,000 times the mass of the Earth. Another thing we can relate to is Jupiter. Jupiter is what's referred to as a gas giant. It's also a ball of mainly hydrogen gas. However, it is not massive enough to actually ignite in the same way that our sun does. Jupiter is 300 times the mass of the Earth, but you would need 1,000 of them just to have the same mass as the sun. The sun is very, very big, and it's one of the things that contributes to it igniting. There are a great deal of stars. Astronomers have been categorizing and organizing things, and we've kind of discovered there seems to be a trend into how a star works or how it looks. This trend is described by the Hertzsprung-Russell diagram. It shows these patterns. So our sun happens to be along the main sequence. It's in here. It's a yellow star for what it's worth. And the main sequence of stars kind of looks a little bit like this. And then you have these other things. You have blue giants, and you have red giants, and then you have red supergiants. You have white dwarfs. And so all the stars that we see fit into these kind of categories, if you will. You'll also note here that we talk about this particular graph. You'll notice that the temperature itself is increasing as we go right to left. That's not normally how we draw our graphs. So we could say that as we move along the main sequence here, the temperature is increasing as we come back right to left. We can notice that by the x-axis here. So one of the cool things is that the hotter something is, the bluer it glows. And the cooler something is, the redder it glows. And you've seen this before. You've seen this anytime you've heated up a electric stove coil or the oven itself. The actual coils will glow red. They're hot, but they're not that hot. They're roughly around this hot, as you can see here. So they're getting up to temperatures that allow them to glow red. If you were able to make the oven heat up even more, it would go from red to orange to yellow and then finally to blue. You may also notice this phenomenon when you look at fire, in terms of like maybe a campfire or something. If it's burning very, very hot, the very middle and base of the flame is sometimes a bluish color, or maybe a yellowish color amongst the flickers of red. So everything kind of fits into here. Now you also have these things called red giants and red supergiants and blue giants, and they're related to the main sequence stars, and I hope you see that too. And so are the white dwarfs. In order to see how they're related, it would be good for us to look at the lifetime of a star, and we're going to do this in a few different iterations. And the first one is the main sequence. So it kind of starts off a little like this. At some point in time, there was some hydrogen gas, and no matter how much time it took, gravity seems to pull the gas together, and it coalesces in a small area. And this area we actually have a name for it. It's called a nebula. Um, but as the gas builds up, so too does its gravitational pull. So gravity pulls things together, but gravity also is better and better at pulling things together the more massive something is. And so the more massive it is, it can pull more gas in, and then more gas leads to more mass, and more gas leads to more mass. And while all of this is happening, the temperature is rising ever higher. You can see that you can change the temperature of something by putting more pressure. Just go take an ice cube and squeeze it before your hands, and it will eventually melt. So that being said, I'm just presenting you the idea that as this gas is becoming more and more condensed and it's accumulating more and more gas, its temperature is increasing, and by the time it hits around 10 million degrees Celsius, the hydrogen gas that is being coalescing ignites. Not how we typically ignite a fire, however. This process is a little bit different. And so here are some pictures of nebula that, or nebulae in plural, that the Hubble Space Telescope has taken pictures of. And so we've kind of named them after what we think they look a little bit alike. So we have the Crab Nebula, the Cat's Eye Nebula, sometimes just referred to as the Eye Nebula, and then the Eagle Nebula. Now that last one there, the Eagle Nebula, probably one of my more favorite pictures, but that one there is taken in infrared, and so it looks a little different if you take it in different images, in different perspectives. So for example, this is also the Eagle Nebula. So you can see it's this coalescence of gas. Sometimes what happens next is kind of interesting to describe. So at the 10 million degree mark, the mass is so much that gravity pushes the hydrogen atoms so closely together. Now hydrogen, if we remember from our periodic table, it's the most basic atom. It's one proton, it's one electron, and at this temperature, the electrons are just gone. They've been stripped away. And really all that matters here is that the hydrogen nucleus is becoming so... Well, what's in the hydrogen nucleus? It's just a proton. So I'm going to now refer to it as a proton. One proton is being so closely put together to another proton. They should want to push against each other. The electric force will keep them from coming together. But no matter what happens, if there's enough gravity, even that electric force is overcome. And those two protons that normally would be resisting each other through the electric force will fuse. And so those two protons, those two hydrogen, they fuse together and they'll produce helium. And this process fundamentally releases energy. And it pushes back against gravity. We call this the radiation pressure. Sometimes it's referred to as the outward pressure of a star, or the pressure due to nuclear fusion. And that's what we're talking about here. We're talking about fusion. The stars themselves fuse things together. And eventually, all of that hydrogen, lots of it anyway, the majority of it, will begin to run out. Once all of that hydrogen is fused into helium, the outward pressure of fusion begins to drop off and cease altogether. And then gravity will want to pull everything together. There's that much mass still there. The mass didn't go anywhere. It just changed from hydrogen to helium. And the star begins to collapse. But if there's enough gravity, which for most main sequence stars there's enough gravity that the helium itself will start to be pushed so close together that it undergoes fusion. Fuses into some other elements, and that fusion pressure prevents that collapse from happening. let's take a minute and just talk about our own sun, because there's an interesting thing that happens when the hydrogen fuel source is depleted. And those red giants we saw in that diagram, that's kind of where they come from. When the main sequence stars run out of hydrogen, they start to fuse helium, and that pressure makes the star swell. Its size, its volume increases. It's been looked at that other stars like our own that have gone to the red giant phase swell so much bigger, and actually the sun's surface will be where the Earth is currently. So when the sun becomes a red giant, the Earth will be engulfed in the sun. This is kind of set to happen in around 5 billion years. So we've got lots of time. But the fusion of helium begins to create heavier elements. Elements such as carbon and oxygen. And this begins to mark the end of the star. Now the red giant will eventually start to run out of helium to fuse. The outward pressure no longer is keeping the star upright, and the gravity wins the battle. Well, maybe the star will start to fuse carbon and oxygen. It turns out that for most main sequence stars like our own sun, there just isn't enough mass to fuse the carbon and oxygen together. All of this is dependent on how much mass there is. And for our star, when it comes into the red giant phase, it starts to run out of helium to burn. It won't be able to fuse the carbon and the oxygen. There just won't be enough gravitational mass to push them close enough together. Without any fusion occurring, gravity will win this battle. Gravity will compress the star. It will begin to shrink into a remnant of its former self. We call that a white dwarf star. Now the white dwarf star we also saw that on the actual Hertzsprung-Russell diagram. That was one of the other types of stars that we've seen. So the white dwarf is essentially when the red giant can no longer fuse anything anymore. And so the white dwarf star, in fact, eventually turns into a black dwarf star as its brightness just slowly fades over time. The white dwarf star will retain around 50% of the mass as it shrinks, and the other half is just ejected into the solar system. All that carbon and oxygen ejected into the solar system. So, another fun fact. It turns out that that Hertzsprung-Russell diagram, we never actually see any black dwarf stars on that. And we've done a little bit of math that kind of says that, well, the time it would take for the white dwarf star to actually fade so much that it becomes a black dwarf star is estimated to be longer or more time than what the current age of the universe is. So there are no black dwarf stars. There just hasn't been enough time for the white dwarf stars to fade yet. But eventually. Okay. Here we have the life of a star. Part 2, if you will, or massive edition, part 1, because the life of a massive star begins as does a sun-like star, like our own. However, when a star has accumulated so much mass that its mass is around 10 to 30 times that of the sun, our own star, The beginning is roughly the same, but the end is different. Instead of expanding into a red giant, it expands into a red supergiant. And the star has enough mass that gravity pushes so very intensely that during this phase, it's able to fuse things from carbon and oxygen. So it's able to produce some of these elements we are familiar with, like aluminum and calcium and potassium and neon and iron. And eventually the core, the center of the red supergiant, becomes very rich in iron. And as the fuel for fusion is exhausted over time, as it's fusing all the hydrogen, it's fusing all the helium, it's fusing all the carbon, it's fusing everything up until it gets iron, the star becomes more and more unstable. And the process itself actually stops at iron. You see, a star can't efficiently fuse iron. It's the nature of the elements themselves. Instead of releasing energy to fuse iron, it would have to take up energy, and so it just simply doesn't. As fusion ceases, the star collapses, and the gravity is actually so intense in the core that it crushes the electrons so close to their nucleuses that they fall into protons, forming neutrons. The outer shell of the star then bounces off the core so violently that all the elements that are heavier than iron, think of those, gold, silver, lead, that's where all those elements are created. This process doesn't take that long. We call this process a supernova. And in this case, what's left over when those electrons fell into the protons, forming neutrons, what's left over is a neutron star. And you may not realize it, but I've actually already shown you what a supernova looks like. At least I showed you what was left over of it. We've documented this ourselves here on Earth. Astronomers, people really all over the world, in 1054 AD, they noted a new star was in the night sky. A new star that was present for around 2 years before it disappeared. It turns out that this was in fact a supernova because we looked centuries later and we saw this. We saw the Crab Nebula. At the center of the Crab Nebula, a collapsed star. The ejected shell of a supergiant actually forms a nebula. And the nebula is the birthplace of stars. Nebula is where our star formed. It's within the supernova that you get many elements. It's within the red supergiant that you get many more elements. From the red supergiant all the way through to the supernova that happens from it, you get all kinds of elements. Gold, silver, uranium, lead, calcium, potassium. Everything that actually makes up you and our planet is, well, that's the leftovers. Carl Sagan said it pretty well. He was an astronomer. He said the nitrogen in our DNA and the calcium in our teeth, the iron that allows our blood to bond to oxygen, the carbon, the apple pies, all of those elements are made in the interiors of collapsing stars. His famous quote, "We are star stuff." Okay. The Life of a Star, Massive Edition, Part 2. let's recap a few things. Okay, mass means more gravity. Within the atoms are the electrons, protons, and neutrons. During stellar collapse, during the collapse of a star, mass dictates the fate of the star. And so, with a star that has the mass of our own sun, the negatively charged electrons pushing on each other, they help to hold the white dwarf star up against gravity. Gravity wants to compress things more and more and more, but something's holding it up, always. In stars like our own, when its life is done, the electrons will hold it up against gravity, pushing back. Like we just saw, for stars 10 to 30 times the size of the sun, the electrons can't hold up against gravity and they fall into the nucleus. The star becomes a neutron star, but the neutrons also push against each other. They fundamentally hold the star up against gravity. But there does exist a certain amount of mass where not even the neutrons can stop gravity. 40 times the mass of the sun. If gravity compresses that, not even neutrons win that fight, and the star is crushed into a black hole. A black hole is the remnant of a star so massive that light itself does not escape its pull. And if light's not escaping that gravitational pull, you actually can't see it. It's not emitting any light. But you can see the influence around it. So these are kind of the same videos. We'll play them. Watch the stars. Just watch the stars. This is the most profound one that whips around. These are also those trajectories. They think the stars were the black holes, if that makes sense. So, that's a black hole. And this is actually the first photo ever imaged of a black hole. It's taken April 2019. It's the first real image. And so you see here, that might be the center of the black hole. All of this is where a bunch of dust and gas is falling into the black hole. As it falls in, gravity is so intense that it heats up and emits light. And now light can't escape from the center of the black hole, but things around the black hole will emit light. And it's kind of a nice picture, even though it's kind of grainy and blurry. Maybe we'll have better ones in the years to come. That would be nice, actually. That being said, this should be everything you need to know about stars, the birth of stars, and their subsequent collapse and death.